speaking to us on the capacity of the range and the Wiener sausage.
Okay, thanks a lot for the invitation. It's a great pleasure to be here. So I'm going to talk about some recent work which was done jointly with Amina Selah and Bruno Shapira, where we studied the capacity of the range and the Wiener sausage. So first I'm going to fix some notation and give some definitions. Then I will mention some background and history for the problem, and then I'll mention our results, and in the second part of the talk I'm going to explain some proof ideas. So I'm going to be interested in Sn, which is going to be a simple random walk in Zd, and I'm going to focus in the transient dimension d greater than or equal to 3. And Rn is going to denote the range of the walk by time n. So it's the set of points S0 up to Sn. So it's the set of visited points by the walk up to time n. So I'll call that the range. Okay, so let me say a few words about the size of the range. So this has a long history in probability, and I'll just mention some references. So the first reference is by Dvoretsky and Erdos from 51. So they obtained a strong law of large numbers for the size of the range in all dimensions d greater than or equal to 2. For Rn, for all d greater than or equal to 2. In dimension 2, they showed that the size of the range divided by n over log n converges to some constant, almost surely. And in higher dimensions, d greater than or equal to 3, it grows, the size of the range grows linearly in n. And CD is a constant that depends on dimension. Okay, so Dvoretsky and Erdos obtained the strong law of large numbers, and then Jain and Ori and Jain and Pruitt in the 60s and 70s. They obtained a central limit theorem for the size of the range, CLT, for all d greater than or equal to 3. So just a standard CLT, which means that the size of the range centered, so minus the expectation divided by the square root of the variance, converges to a standard normal. For d equal to 3, the variance of the size is of order n log n, while for d greater than or equal to 4, it's of order n. And then the two-dimensional case was treated by Legal in '86, who showed so d equal to, so he showed a non-conventional CLT for the size of the range. So when I say non-conventional, I just mean that the limit is non-Gaussian, and the limit is the so-called self-intersection local time for Brownian motion, and it's non-Gaussian. So I don't want to state the result of Legal right now, because I'll come back to it later when I want to show the analogy to our results. And in the two-dimensional case, the size of the range, the expected size, is of order n over log n, and the variance is of order n squared over log n to the 4. Okay. So this is all of this is about the size of the range. So how else can one think about the size of a set? So if we have a set A, then one way to think of the size of a set is by throwing a random point and looking at the probability that this random point falls in A. That's one way to think intuitively of the size of a set. And now, if we replace the word random point by a random curve, which could be either a random walk path or a Brownian motion path, then this gives rise to the capacity of the set. So I'm going to define the capacity in a few minutes formally, but I just want to give this way of thinking of capacity in terms of probabilities that a random walk path or a Brownian motion path hits a set. And the reason I say that is because so a point is 0-dimensional, while a Brownian motion path is 2-dimensional in dimensions 2 and higher. So heuristically, one would expect that the properties of the size of the range in dimension d should correspond to the properties of the capacity of the range in dimension d plus 2 because of the drop of 2 dimensions here. So this is just a heuristic, but I'm going to explain this how we actually confirm that in a certain sense by studying the capacity of the range. And another example which has the same flavor of the drop of 2 dimensions, but it's completely different to this setting, is the theorem by Cisialke and Taylor from the 60s, who showed that the occupation time of the unit ball by a d-dimensional Brownian motion has the same law as the exit time from the unit ball of a d minus 2 Brownian motion, by a Brownian motion in d minus 2 dimensions. Okay, so now I guess I'll write here. So now let me give the formal definition of capacity. So first, in the discrete setting, so if we have a set A, subset of ZD, which is finite, and we are always going to be transient from now on, then we define the capacity of A to be the sum over all x in A of the escape probabilities from A. So HA plus is the first n after time 1, so that Sn is in A. And another equivalent definition of the capacity in the discrete setting is as the limit, as the norm of x goes to infinity, of the probability starting from x that we hit the set A divided by the green kernel at x. So here, when I put the plus, I start from time 1, and without the plus, it starts from time 0. And g of x is just the green kernel on ZD, so just the expected number of visits to x when a random walk starts from 0. And we are transient. Okay, so I'm going to show this equivalence afterwards. It's really, really simple to show it. But this expression here is much more useful in what I'm going to do. And another reason I really like this expression is because, for instance, you can immediately see the monotonicity property of capacity when a set A is a subset of B, that the capacity increases, which is not clear from the first expression immediately. Okay, that's the definition in the discrete setting. Now, in the continuum, so one way to define capacity is again in this way, where now HA denotes the first heating time of the set A by a standard Brownian motion. And so by star for a Brownian motion. So G of X is the green kernel of the Brownian motion now. And there is also the variational characterization. So the capacity of A is the inverse of the integral of the green kernel with respect to all measures mu that are probability measures supported on the set A. Okay. Okay. So now let me give a little bit of motivation why one is interested in studying capacities of a set. So the capacity of a set is a central notion in probability which appears in many unexpected settings, and just right from the definition one can see that it's related to intersection probabilities. So understanding capacities is equivalent to understanding intersection probabilities and vice versa. The first result of this flavor goes back to Kakutani from 45 approximately, who characterized polar sets for Brownian motion. So he gave a criterion for which sets are not hit by Brownian motion. They are the sets that have zero capacity. And since Kakutani, there have been more quantitative estimates, more quantitative statements. So there is a paper by Benjamin, so let me just write Kakutani from 45, and then there is a paper by Benjamini, P. Mantle, and Perez, which is called Martin capacity for Markov chains, and they show that if you have a transient Markov chain, then the probability that it hits any given set is upper bounded by the capacity of the set with respect to the Martin kernel. I'll say what it is, and it's lower bounded by half times this capacity. So the Martin kernel is just the green kernel of the Markov chain normalized with respect to the starting point. Okay, so the capacity has also been used in the definition of random interlacements by Snitman. And more recently, there has been some work of Tom Hatchcroft, who calculated critical exponents for uniform spanning forests in dimensions 5 and higher, and so d greater than or equal to 5 uniform spanning forest. And now together we are looking at dimension 3 and 4, and we are trying to understand now the capacity of the loop erased random walk. Okay, so he has reduced the problem of calculating critical exponents to the question of understanding capacities of loop erased walks. Okay, so now that I have defined capacity, we can look at the capacity of the range of the walk. This is a random variable, and if we divide by n, this converges to some constant, gamma d, almost surely. This was proved by Jain and Orey, and they established that this constant gamma d is positive if and only if d is greater than or equal to 5. So this is a strong law of large numbers, and this was proved in the 60s, I think. And so the next natural question is, once we have a strong law of large numbers, is there a CLT? And this was our first result with Amin and Bruno. So let me just write. Sophia and me. So we showed that a CLT holds for all d greater than or equal to 6, just a standard CLT. So for d greater than or equal to 6, so I'm talking about the capacity here. And for d greater than or equal to 6, the variance of the capacity grows linearly with n. And we couldn't do the 5-dimensional case. We have a lower bound on the variance, which is n, but we expect it to be of order n log n, in analogy to the variance of the size of the range in 3 dimensions, which is also n log n. Okay, so in this first paper, we conjectured that in 3 dimensions, there should be a distributional limit. And for 4 dimensions, we showed, so this is for d equal to 4, we showed that the expectation of the capacity is asymptotic to pi squared over 8 times n over log n. So this is a straightforward application of the estimates by Lawler, who calculated very precisely the probability that a two-sided walk does not intersect a third walk in 4 dimensions, and he also has the exact constant, which is pi squared over 8, so this is completely straightforward. So then we conjectured that we should also have a strong law of large numbers in 4 dimensions. And then a bit later, Yin and Chang showed indeed that in 3 dimensions, the capacity normalized by root n, this is the expectation, converges to some constant times the capacity of the path of Brownian motion. Vita is a 3D Brownian motion in distribution. And then in 4 dimensions, he proved convergence in probability. Okay. And then we focused more on the 4-dimensional case. And so I'm just going to abbreviate our names by ABP. So for the 4-dimensional case, we focused on 4 dimensions. First of all, we upgraded the convergence in probability to almost sure convergence. So the capacity divided by n over log n converges to pi squared over 8, almost surely. But most of the work went into proving a CLT, which is again non-conventional. So we showed, I'll write it here. So what we showed is that the capacity centered, so minus the expectation, divided by n over log n squared converges in distribution to minus 4 pi squared times gamma g of 0, 1 squared. So I have to tell you what this gamma g is. So first of all, this is non-Gaussian. And now I'm just going to write a formal equality for this gamma g. So this is now a 4-dimensional Brownian motion, and G is the green kernel for Brownian motion. And so here I'm integrating time from 0 to 1 twice, and I look at the green kernel of vita as vita t, and here I'm subtracting the expectation. So I said this is, I put it in quotation marks, this is only a formal equality. The reason is that both terms are infinite, so one cannot really write this down. But there is a limiting procedure that one can follow to make sense of this random variable, which actually also exists in L2. And now I would like, one more thing. So I said this is non-Gaussian, the reason being because it has some infinite exponential moment. And now I would like to mention, to come back to Legal's result that I wrote up there. And I would like to mention the analogy. So earlier I said that we expect the properties in d dimensions for the capacity to correspond to properties in d minus 2 for the size. And so what Legal showed in his work is that the size of the range centered, so d equal to, again divided by n over log n squared, converges in distribution to minus pi squared times gamma. I'm going to write delta 0 here of 0, 1 squared. So what is gamma delta 0? This is, I just replace this green kernel by the Dirac mass at 0. And again, for the case of delta 0, this is a formal equality, but in the same way as Legal worked to make sense of this variable, we also work to make sense of our variable. And this is what I wrote before. This is called the self-intersection local time, and also in this case, this is non-Gaussian. Okay. So I just want to mention one final result, which concerns the Wiener sausage. So just like for the size of the range and the volume of the Wiener sausage, Legal had to work, he had to work separate, to use different arguments for each of the two. The same thing holds for the capacity, and we cannot deduce the strong law of the CLT directly from the discrete results. So if we take the Wiener sausage to just be the Wiener sausage of radius r, I just run the Brownian motion path for time t, and then I put balls around it, and I take the union of all these balls. This is what is called the Wiener sausage. And so in 4 dimensions, we obtained a strong law of large numbers. So we showed that the capacity divided by t over log t converges to some constant, I don't remember the constant. And the convergence holds almost surely, and in LP for all p in 1 infinity. So we were not able, we haven't tried hard to obtain a CLT in the Wiener sausage case. So here, let me just say that this is for all R positive, and this C is independent of R. This is analogous to the size of the volume, to the volume of the Wiener sausage in 2 dimensions, which is also independent of R. And here it's because of the scaling of the capacity, which agrees with the Brownian scaling in 4 dimensions. Okay, so this result answers a question of Vandenberg, Bolkhausen, and Frank den Hollander, who studied what they call the torsional rigidity of Brownian domains. So if you have, so you take a Brownian motion on the torus, and then you consider for any domain of the torus, the torsional rigidity of this domain is simply the integral over all starting points in the set of the expected lifetime in the domain by a standard Brownian motion. And they studied the torsional rigidity of a Brownian domain, so the complement of a Brownian part or a Wiener sausage. And they reduced the question of understanding the expected torsional rigidity to showing concentration of the capacity of the Wiener sausage. Okay, good. So in the remaining part of the talk, I would like to explain some of the proof ideas, mainly behind in the discrete setting. So I want to give some heuristics why this is the correct scaling to expect in 4 dimensions. So before I do that, before I look at the capacity, I want to take a small detour and go back to Legal's proof from the 80s. So Legal, how did he show the convergence for the size of the range? So the starting point is to decompose the range up to time n into 2 sub-ranges, up to time n over 2, minus the intersection of the 2. So now, because these 2 ranges here concern disjoint intervals of the walk, this is the range of one walk plus the range of an independent walk run for time n over 2 minus the intersection. So we start with the size of the range, we decompose into the sum of 2 independent ranges, and we subtract the intersection. And then we continue in the same way. So eventually, we're going to get that the size of the range is the sum of n over, I just fix some p. So I is going to go from 1 up to 2 to the p. So I subdivide in intervals of length n over 2 to the p, minus some term that I call chi n. So first of all, these are all independent ranges because of this decomposition. And now chi n is just going to be, it's a complicated term. It contains all possible intersections. So we subdivide in half, we look at the 2 parts, and then each part subdivide in half, and then look at all possible intersections, and so on. So it's a complicated sum of all possible intersection terms. So this is chi n. So what Legal showed is that, so this sum is a sum of IID terms. So this dominates the law of large numbers, and this chi n dominates the fluctuations. And so to finish the proof, then one has to calculate all moments of chi n and show that they converge to the corresponding moments of the self-intersection local time. And that's the proof of Legal. So what is very nice about the size is that one has this decomposition. And so we would like to do something similar for the capacity. So first we would like to prove a similar equality for the capacity of the union of 2 sets. So, first of all, I would like to explain very quickly the second formula for the capacity as the limit of heating probabilities normalized by the green kernel. So, the probability that we hit a set A starting from X, we are in the transient case. So, I'm just going to write down the last exit decomposition formula. So it's the sum overall y in the set A of the number of visits to y times the probability starting from y that we never come back to A. And so now if I divide by g of x, both sides, and I take the limit as x goes to infinity, this is going to converge to 1 as x goes to infinity. So this whole sum is going to converge to the capacity of A. So the capacity of A is given as the limit of this probability. Divided by g of x. Okay, so now, as I said, I want to obtain a similar decomposition formula for the capacity of the union of two sets. So let me take the capacity of the union. So this is this limit where I replace A by A union B. So if I now write the probability that H of A union B is finite, this is going to be HA finite plus HB finite minus the intersection of these two events. Now, if I divide by g of x, both sides, and I take the limit as x goes to infinity, the first term is going to go to the capacity of A. The second term is going to go to the capacity of B. And now this term is lower bounded by the probability that we hit the intersection of A and B. And here we have a minus. So what we showed is that the capacity of A union B is going to be upper bounded by the sum of the capacities minus the capacity of the intersection. Dividing by g of x here, this is going to go to the capacity of the intersection. So what I obtained here is a very classical inequality for capacities, and the way I obtained it was simply by lower bounding this probability by the probability that we hit the intersection. And unfortunately, in 4 dimensions, omitting all of these terms that we are lower bounding by this probability is very costly. So instead of getting this inequality, we can actually obtain an exact equality. So I'm just going to write this term now. So HA finite and HB finite. So either we hit A before B, or we hit B before A, and I have to subtract the probability that we hit them both at the same time. So this is going to be negligible when I divide by g of x afterwards, because again it will be bounded by the capacity of the intersection, which is very small in the case we're interested in 4 dimensions when A and B are 2 independent ranges. So I'm just going to treat each of these 2 terms, but they are symmetric, so I'm just going to look at the first term. So the probability that we hit A first, so this is immediate. I'm just going to sum over all of the hitting points So I'm summing over, so since I want to hit A first, the first hitting time of the union will happen in A, and this will happen in finite time, and then we want to hit B, and then I conditioned and I multiplied by the probability that we hit the union in finite time. And now we want to divide by g of x. So, and let x go to infinity. So this term is going to go to the capacity of the union. And as x goes to infinity, this is going to go to the harmonic measure from infinity. So the probability starting from y that h a union b plus is equal to infinity divided by the capacity. And so the capacity is going to cancel from these two terms. And so what we get is that in the limit, this term is going to give us the sum over all y in A of this probability and then we have to multiply by this probability as well, the probability that we hit B. And now I'm just going to do another last exit decomposition. So I'm going to take the sum over all B of g y z times the probability starting from z that h b plus is equal to infinity. And I'm going to call this sum chi ab. Okay, so what we obtained is that the capacity of the union So we showed that the capacity of the union is the sum of the capacity of A plus the capacity of B minus this term and minus the symmetric one, chi BA, plus some small term epsilon that I'm not going to care about. This comes from this last term here, but we can safely forget about it. And chi is this expression that I wrote here. So now we have an exact equality for the decomposition of the union of two sets. And now we want to go back to study the capacity of the range. So again, we do the subdivisions like Legal. And so we're going to get that the capacity of the range is the sum of the capacities of independent ranges run for time of walks run for time n over 2 to the p minus, I'm just going to write it again as a term chi n, and this term chi n is going to include all of these terms here. It's going to be the sum of all such terms, where in the first scale A is going to be the first range for time n over 2, and B is going to be the remaining part, and then we keep subdividing, so then it's all possible combinations of such sets. And just like in Legal's case, this is going to give the Strong-Leflertz numbers, and this will give the fluctuations. And I promised I'm going to explain where the n over log n squared comes from. So in the remaining few minutes, I'm going to explain where this comes from, and I'm not going to look at this term chi n, but I'm just going to look at the first scale. So when we subdivide in two, and we consider chi of the first part together with the second part. And then to complete the proof, one has to show that all moments of chi n converge to the corresponding moments of the gamma g quantity that I wrote before. So this is very technical, and I'm not going to get into that. Okay. So as I said, I'm just going to look at the first scale. So I'm going to look at chi of, instead of looking at time n over 2, I'm just going to look at time n. Chi of Rn, and Rn tilde, where these two are two independent ranges. So, okay, I erased the expression that I obtained for chi, but I'm just going to write it here. So if you haven't taken notes, you won't remember one term that I'm going to omit now. So h of Rn plus equal infinity, g of xy, py h of Rn tilde plus equal infinity. So before, I had written here, so this was A and this was B, and I had written Rn union Rn tilde, but we can just forget about Rn tilde in this first term, and we don't lose much. So these here are now random variables. I just don't want to condition on Rn, but this one is a random variable of Rn and this one of Rn tilde. Okay, so I want to get the order of chi of Rn, Rn tilde. So I wrote before that the expectation of the capacity in 4 dimensions is of order n over log n. Let me write it here. So this is here actually. The expectation of the capacity is this constant, doesn't matter, times n over log n. And the capacity is, so what I'm going to write now is just heuristics, it's not rigorous at all. So the capacity is the sum over all x in Rn of the escape probability from Rn. Okay, and so we know that this sum is of order n over log n, and the size of the range in 4 dimensions grows linearly with n. So one would expect that for typical x in the range, this is going to be of order 1 over log n for typical x in the range. Okay, so if we agree with this heuristic, then this first probability will be 1 over log n, same for the second one. And so what we are going to get is that this is going to be the sum of, let me write here, 1 over log n squared of gxy. And now I'm taking the sum over all x in Rn and y in Rn tilde of gxy, which I can write as the sum from 1 up to n, and now L from 1 up to n of gsk SL tilde, where these two are independent walks. Now, if I divide by root n, it's going to come up. So I'm going to multiply by another n here, and I'm going to divide by 1 over n squared. So this one with this one will cancel the n squared. Okay, so we get the n over log n squared that I wrote before, and now this quantity here, by just Donskoy's invariance principle, converges to the corresponding quantity for 2 independent Brownian motions, g vita s vita tilde t, ds dt between 0 and 1. And so what we showed is that this, in the first scale, chi of Rn, Rn tilde is asymptotic to 1 over log n squared, n over n log n, n over log n squared times this integral. And in order to complete the proof, as I said, one has to look at all of the possible subintervals. And so here we obtain that for 2 independent Brownian motions, which is the same as looking at one walk up to time n over 2 and the other walk for the remaining interval. And then if we keep subdividing, then we are just going to get in the end the whole interval, because this would be actually 0 to a half for the first scale, because we look up to time n over 2. And I think I'll stop here. Are there any questions? Yes.
In your subdivision process, how do you choose the P until which? Because you don't want to get to the end, right? You don't want to take P.
Oh, here. Right. So first we let n go to infinity and then we let p go to infinity. It's exactly the same as legal.
Is there a way to get an expression for sort of gamma in terms of limiting behavior of some intersection or self-intersection of mesoscopic sausages, Wiener sausage?
So
Because I mean, somehow what controls the thing now is probably that there will be loops of size of order log n, where things are, I mean, long loops where the starting and end point are, they are not identical, but they will be still fairly close.
right.
So, is there any hope for?
So you see how we obtain you know how to obtain the limit, of course. But you're saying, yeah.
So there's no way to have another. Another question would be, so in the Gauss result, he has all the whole expansion, right? So
Right.
But here, is there some reason why this would probably not work, or whether this might?
Right. So actually, Yves Lejean asked me the same question,
Okay.
and we haven't thought about that. But yes, I don't know. But I think it's a very interesting question to look at. Okay.